Welcome to the D60 Relay. This training course will provide you with an in-depth understanding of the theory behind distance protection, while describing the function of all of the main elements that are available in the D60 Relay. You will learn through an interactive approach, which uses animation and real-world examples to convey these concepts in a way that is not possible through other mediums. Another valuable resource that can be used in conjunction with this CD is the Universal Relay Applications 1 Learning CD. This CD delivers the fundamentals of the UR platform. Some of the concepts and examples covered within this CD build upon those demonstrated within the UR Applications 1 CD. This course will begin with a basic review of transmission line theory, and then move on to describe some of the various instruments that the D60 uses to measure the current and voltage magnitudes of the line. Then the student will proceed through the fundamental theory of distance protection and the different types of distance protection zones that are commonly used. The next section will demonstrate how to configure all the necessary zones of protection in the D60 Relay. You will learn how to set up both MO and quadrilateral zones of protection for both ground and phase distance applications. We will then proceed to discuss and configure all of the different teleprotection schemes that are available in the D60 to speed up the clearing of transmission line faults. Finally, we will cover all of the control logic and functions that are available to complete your understanding of how to use the D60 for a transmission line application. We will start this section with a brief overview of transmission lines and their general operation and characteristics in a power system. A transmission line is a circuit that is used to transmit power from one location to another and can span short distances in the magnitude of a few hundred meters, or very large distances in the magnitudes of hundreds of kilometers. Transmission lines that are protected using distance relays are usually at least 1 kilometer in length and can extend as far as 750 kilometers or more. Transmission lines consist of conductors that are supported by a structure to hold the conductors high above the ground. These conductors are connected to the structure using devices called insulators, which make sure there is no electrical connection between the conductors and the supporting structure. The material that is used in the structure, the physical arrangement of the components used, and the geography that the conductors and towers are located in greatly affect the electrical properties of the line. All of these factors must be considered when determining the best method of protecting this transmission line. For example, wood pole lines tend to have a much larger zero-sequence impedance than a steel tower line will. Since this impedance is much larger, the total impedance to ground is also generally larger, which may cause problems for a ground distance element. In a case like this, you may need to change your protection scheme to include an additional directional ground overcurrent element to find an effective solution. In a power system, the area that constitutes a transmission line has well-defined boundaries. The physical location of a line boundary is often called a terminal. Terminals classify the end of a transmission line and can be a switch, a breaker, a bus, or a transformer. There are 4 main classifications of transmission lines that describe their configuration, the function they perform, and their location in the system. Parallel lines describe a configuration where multiple transmission lines run side by side. This is done to transmit large amounts of power from one location to another, and to have redundant paths for current in case one of the lines were shut down due to a fault. Interconnector transmission lines are used to connect one section of a power system to another. Generator export transmission lines are used to transmit power from a generating station to the rest of the grid. Process plant load transmission lines are used to transmit power from a transformer or switching station to a large industrial complex. Transmission lines are classified into 3 categories that describe the presences of generation or of possible sources of fault current that might be found at the transmission line's boundaries. These are single-ended, double-ended, and multi-ended. A single-ended line, also called a radial line, has a source at only one end. This type of line is used to deliver power from the source to a load at the other end of the line. Obviously, whenever a fault occurs, there is only one source of current to feed the fault. A double-ended line has only 2 boundaries, each of which can have a source of fault current available. This type of line is used to deliver power usually in different directions at different times. If a fault occurs on this transmission line, current will be fed to the fault from 2 locations. A multi-ended line has more than 2 boundaries, each of which can have a source of fault current available. For this type of line, the direction of normal power flow can be highly variable, and at the time of a fault on the transmission line, the fault will be fed from many different locations. Sometimes the transmission line itself will be tapped to provide a source of power to a load. Distance protection is one method of protecting a transmission line in this configuration and will be covered in detail later in this course. The voltages that are used for transmission of power over transmission lines are split into three categories. These are distribution levels, which are in the range of 2 kilovolts to 50 kilovolts. Sub-transmission levels, which are in the range of 30 kilovolts to 150 kilovolts. And transmission levels, which are greater than 100 kilovolts. Most applications that use distance protection are 50 kilovolts or greater. Transmission line lengths have also been classified into three categories. Short transmission lines are less than 80 kilometers in length. Medium transmission lines are roughly between 80 kilometers to 240 kilometers. Long transmission lines are greater than 240 kilometers in length. Another factor of transmission lines that is useful to note is the occurrence of shunt capacitance on a line. Normally, transmission lines have a certain amount of inductive losses due to the inductive nature of transmission lines. This vector diagram shows the effect this inductance has by adding negative megavars and moving the current and voltage away from unity power factor. Shunt capacitance occurs between the transmission lines and the ground. This capacitance counterbalances some of the inductance by adding leading megavars on the line and helps bring the current and voltage back to unity power factor. Typical three-phase megavar values are 1.3 to 1.5 megavars per kilometer for 500 kilovolt lines, and 0.15 to 0.4 megavars per kilometer for 230 kilovolt lines. Caution needs to be taken when transmission lines are used with high voltage potentials. Due to the Ferranti effect, the shunt capacitance on the line can become so large that the voltage on the far end of the line can rise higher than the normal line potential. The importance of transmission lines in a power system is quite evident. They are responsible for transmitting large amounts of current at possibly very high voltages. If a fault occurs on a transmission line and it is not cleared properly and quickly, the stability of the entire system can be compromised. The longer that the fault is allowed to remain on the line, the higher the possibility that the system will become unstable and possibly collapse. Calculating the magnitude of current that will flow through the transmission line at the time of the fault and configuring accurate settings for distance relays is very important in properly protecting your transmission lines. In order to appropriately do this, we must first calculate the system impedance ratio and develop an equivalent electrical model of the transmission line. The system impedance ratio is a factor that needs to be considered when determining how to protect a transmission line and can greatly affect what will happen to a power system at the time of the fault. The system impedance ratio takes the source impedance, which is the source impedance of the system behind the transmission line, and divides that by the line impedance that you are protecting. If the system behind the transmission line has a strong source, the source impedance will be low. In this configuration, if a fault occurs on the transmission line, the fault current will be very high, and the voltage at the location of the PTs will tend to remain stable. If the system behind the transmission line has a weak source, the source impedance will be higher. In this configuration, if a fault occurs on the transmission line, the fault current will be lower in magnitude, and the line voltage at the location of the PTs will tend to drop. As you can see, the system impedance ratio is a very important factor in the stability of a power system at the time of a fault, and must be considered when determining the type of protection needed and the speed that the faults need to be cleared by relaying. If current or voltage levels need to be accurately calculated at any specific point on the line, you need to draw an equivalent model of your transmission line. Different models of transmission lines are used for different lengths of line. These models are in three categories: short, medium, and long lines. The pi model shown here has historically been used for representing medium-length lines. However, using this representation of the line and computer-aided software that is now available, we can accurately calculate all the values for this model for both medium and long transmission lines. Having this data simplifies our task in performing fault calculations and setting up of our distance protection relays. For the general pi model shown here, the following nomenclature is used: lowercase z is equal to the series impedance per unit length per phase. Lowercase y is equal to the shunt admittance per unit length per phase to neutral. L is equal to the length of line. Uppercase Z is equal to the lowercase z multiplied by the length of the line, or L, which is also equal to the total series impedance per phase. Uppercase Y is equal to the lowercase y multiplied by the length of line L, which is also equal to the total shunt admittance per phase to neutral. Transmission lines in fault calculation studies are generally considered to have conductors where all three phases are symmetrical with respect to each other and the ground. That is to say, they have identical characteristics. However, the common configuration where all three phases are hung vertically, as seen here, the characteristics of the different phases are not actually symmetrical due to the difference in height of each phase. This is the reason that some line sections are transposed, where the order of the transmission lines are reversed so that these characteristics differences can balance off and the total line can be approximated as symmetrical. A balanced three-phase system is one in which the phase vectors are 120 degrees apart and of equal magnitude. If either of the two conditions is not satisfied, then the system is considered unbalanced. For any unbalanced system, all three phase quantities can be quantified by using a general analytical technique called symmetrical components. Symmetrical components assume that for all unbalanced systems, the three phases can be represented by a combination of positive, negative, and zero sequence quantities. These sequential quantities can be calculated from either phase to neutral or from phase to phase quantities for voltages and currents. The equations shown here can be used to derive these sequence quantities mathematically for phase and line voltages. A similar approach can be used to yield the current sequence quantities as well. Detailed sequence quantity calculations and their use in fault calculations go beyond the scope of this course. It is just important to note how they are calculated, since we will be making a lot of reference to these sequence quantities later in the course. In order to calculate sequence currents and voltages correctly during faults, the total network sequence impedance of the transmission line system needs to be calculated. The total equivalent network impedance of the system is calculated using the positive sequence impedance, negative sequence impedance, and zero sequence impedance. For transmission lines, under most circumstances, the positive sequence impedance is equal to the negative sequence impedance, and the zero sequence impedance is usually greater than 2 times the positive sequence impedance. However, these values can change depending on the grounding path and the geography of the line. When multiple transmission lines are aligned parallel to one another, their interactions induce an impedance on each other known as the mutual impedance and is notarized as Zm. When this occurs, the overall sequential impedances will be affected in the following manner. The positive sequence impedance will now be the positive sequence impedance of the unparalleled line minus the mutual impedance. The negative sequence impedance will now be the negative sequence impedance of the unparalleled line minus the mutual impedance. And the zero sequence impedance will now be the zero sequence impedance of the unparalleled line plus 2 times the mutual impedance. Typical positive sequence line angles will be in the range of 70 to 85 degrees for lines 115 kilovolts and above. The corresponding zero sequence line angles are rarely the same as the positive sequence values due to the grounding of the line structure. For accurate relaying, these angles need to be input into the relay so the relay can properly model the positive and zero sequence impedances. This wasn't done for older generations of distance relays and is why modern relays, such as the D60, are much more accurate in detecting ground fault. Instrument transformers supply protective relays with current and voltage for measurement. This high current and voltage is first converted by the transformers to much lower quantities that can safely be injected into the relay for measurement. It is important to note that the proper selection of current and voltage transformers for protective relaying applications is the responsibility of the system engineer. The purpose of this section is to familiarize, in a general sense, the different types of CTs and VTs, their connection, and accuracy. CT's introduction. The function of a current transformer, or CT, is to take a current flowing through a wire or cable and step it down to a magnitude that a protective relay can measure. A primary characteristic of CTs is their conversion ratio. In this example, our conversion ratio is 100 to 5. meaning that if 100 amps are passed through the primary phase wire, the CT will scale this down to 5 amps and direct it to the relay via the secondary windings. The 5 amp measure is known as the secondary nominal current. If a fault were to occur on this phase that increases the primary current to 200 amps, then 10 amps would be passed to the relay through the secondary windings consistent with the ratio. CTs have two types of secondary ratings, 5 amps and 1 amp respectively. 5 amps is typically the North American standard, while 1 amp is used in Europe and Asia. Primary ratings are available in various different levels, for example 100, 150, 200, etc. Types of CTs. A common current transformer construction is one in which the power system phase wire is passed through the hole in the center of an annular core or ring, which is called a window. This forms the primary winding. A second insulated wire is then wound around the core and then brought to the relay for measurement. This is known as the secondary winding. A CT with this type of construction is typically referred to as a toroidal or donut style of CT. A bushing type CT refers to a CT that is built into another power system device such as a breaker. Terminals are provided on these devices to permit connecting the CT to a relay. A bar type CT has a solid bar that passes through the annular core to form the primary winding of the CT. The primary phase wires of the power system are then connected directly to these bars to complete the connections. CT classification. CTs are separated into two classifications, metering and protection. Metering CTs are used where a high degree of accuracy is required from a low load up to the full load of a system. An example of a use for metering CTs is revenue billing. These CTs, however, are unable to accurately measure higher levels of power that would happen under fault conditions. CTs for this function are called protection class CTs. Protection class CTs provide a scaled-down current to a protective relay for measurement. These types of CTs deliver a representation of the power system current from conditions near zero current all the way to 20 times rated CT current. The CTs also have an error percentage with a common range anywhere from 5 to 10%. How a CT will operate is listed in two specifications. The previously discussed conversion ratio, for example 100 to 5, 200 to 5, 300 to 5, etc., and the ASA accuracy classification. The American Standards Association, or ASA accuracy classification, contains three characteristics. The first is a number representing the maximum amount of error this CT will produce under a fault condition. In our example, the first number is a 10, indicating this CT will generate no greater than 10% error when transferring the current to the relay. The second designation is a character, which can either be a C or a T. The C stands for calculated, indicating the CT accuracy can be determined using a calculation. This designation was formerly L for low internal secondary impedance. The T stands for tested, indicating the CT accuracy can only be determined through testing. This designation was formerly H for high internal secondary impedance. The final designation is a number that represents the maximum terminal voltage. The maximum terminal voltage is the maximum voltage that is applied across the inputs of the relay when 20 times rated primary current is passed through the CT. Typically, if the error percentage is 10%, then it is normally omitted from the classification, making our example 10C400 appear simply as C400. In order for the relay's measurements to be accurate, the secondary current from the CT must be an accurate scaled replica of the primary CT. For example, if a CT has a conversion ratio of 100 to 5, then the CT must pass only 5 amps of the current to the relay when 100 amps is passed through the CT. The accuracy would be compromised only when a current that is too large for the CT rating is passed through the CT. When this happens, CT saturation occurs. CT saturation can be explained using the graph shown here, displaying the relationship between the secondary current and the secondary voltage applied to the relay's terminals. While in the linear portion, the current and the voltage rise at a uniform rate. When the current and voltage rise above the linear portion of the curve, their relationship is no longer linear. In this case, the current increases at an exponential rate greater than the voltage. The point on the graph where they stop relating linearly is known as the knee or excitation point. We will now give an example demonstrating how a relay will measure a saturated CT. If 100 amps are passed through the CT primary under no saturation, then 100 amps is read by the relay. If the 100 amps, however, causes slight saturation on the CT, the relay's measurement is now decreased, and instead of reading 100 amps, it reads only 50 amps. If the 100 amps cause severe saturation, the relay's measurements are decreased even more, reading only 25 amps. The greater the saturation, the more inaccurate the measurements will be. It is imperative that all measurements being read by the relay are read with an unsaturated CT. To accomplish this, appropriate CT selection must be made to ensure the rated CT can handle the applied current without saturating. CT selection. Proper protection starts with the selection of current transformers. The following is a simple procedure that can be used to check whether or not there is the possibility of CT saturation. This procedure is as follows. The first step is to ensure that the primary rating of the current transformers is equal to or greater than the expected full load current. We can determine the primary rating of a CT by looking at its ratio. For a ratio of 100 to 5, a CT has a primary rating of 100, meaning that no more than 100 amps should be passed through the CT under normal operating conditions. The second step is to ensure that the CT can drive what is called the attached burden at the worst-case fault current levels without saturating. The burden refers to the total load resistance of the secondary circuit. The calculation for the burden is CT secondary resistance, which is the amount of resistance on the secondary windings on the CT, added to the connection wire resistance, which is supplied by the manufacturer, added to the relay's burden resistance, which is the resistance within the protection relay. As explained in the previous section, a CT becomes saturated when the current and voltage secondaries reach the knee point of the excitation curve. To determine whether the CT can drive the attached burden under worst-case fault conditions without saturating, we must determine what the CT's secondary voltage will be at the time of this fault. The CT secondary voltage at the time of fault is equal to the burden resistance times the maximum fault current divided by the CT conversion ratio. The resulting value is then plotted onto the CT excitation curve. If the value plotted on the curve is below the knee point, then the CT will not saturate under these worst-case fault conditions. If the value is equal to or greater than the knee point, then the CT will saturate. Now we will look at a practical example to help us further explain this calculation. Let's assume that we have a motor that draws a maximum full load current of 285 amps. The first step is to choose the appropriate CT. It is customary to select a CT that has a primary rating falling between 50 to 100% of our maximum full load current, in this case 285 amps. Possible CTs for this use would be 300 to 5, 400 to 5, and 500 to 5 CTs, because the primary rating falls between 50 to 100%. In this case, we would select the CT that would fall the closest to 100%. The reason for this is the higher the CT ratio is over the full load current, the less sensitive that CT will be. Since accuracy is always imperative, we will select a CT with a 300 to 5 amp conversion, where the primary rating is 300 and closest to the 100% primary rating. The next step is to ensure this CT doesn't saturate under worst-case fault conditions. If it does, a higher ratio CT, such as the 400 to 5 CT, may need to be chosen. The first step in determining whether a CT will saturate is calculating the maximum voltage that will appear on the primary current of the CT under a worst-case fault condition. The maximum fault current at the load is determined by a fault study, and in this case was determined to be 6,000 amps. Next, we will calculate the secondary resistance, or burden, using the stats provided. The phase CT's secondary resistance, that is the resistance of the windings on the CT, is equal to 0.088 ohms. The length of each wire from the CT to the relay is 50 meters and has a rated resistance of 2.5 ohms per kilometer. The total burden is equal to the CT secondary resistance, which is 0.088, plus 2 times the lead length of 50 meters multiplied by the lead resistance of 2.5 ohms per kilometer, and then divided by 1,000 meters. This is then added to the relay burden of 0.008 ohms, resulting in a total burden of 0.346 ohms. Now the secondary voltage at the time of a worst-case fault can be calculated. First, the total burden resistance, 0.346 ohms, is multiplied by the maximum fault current, 6,000 amps. The result is then divided by the CT ratio, 300:5, concluding that the secondary voltage at the time of a worst-case fault is 34.6 volts. With the maximum secondary CT fault voltage calculated, the final step is to refer to the CT excitation curve. By plotting the 34.6 volts value on the excitation curve, we notice that it falls well below the knee point, indicating that it will not saturate under a worst-case fault condition. If the factors affecting the burden were ever to change, or a higher fault current is measured, these calculations must be repeated to ensure the CT does not saturate. Potential transformers. The next type of transformer we will cover is the potential transformer symbolized as PT, or sometimes known as voltage transformers symbolized as VT. Similar to current transformers, potential transformers scale down the voltage passed through them, as opposed to the previously mentioned current. The scaled-down voltage is then routed to a protective relay for measurement. Also as in current, a PT is classified with a conversion ratio indicating the amount the primary voltage is scaled down. For example, 60:1 scales the primary voltage of 69,000 volts down to 120 volts. There are two different types of potential transformers used today: the electromagnetic voltage transformer and the capacitive voltage transformer. Electromagnetic voltage transformers are usually used when accurate metering needs to be performed for lower voltage applications. Capacitive voltage transformers are commonly used in high-voltage transmission line applications where the voltage is higher than 66 kilovolts. Electromagnetic voltage transformers have dense winding drops designed to accurately scale down the voltage and make sure the ratio is consistent for all variations in the input voltage. Due to the small amount of voltage drops per winding, the electromagnetic voltage transformers will increase in size as the rated primary voltage also increases. Likewise, the cost of electromagnetic voltage transformers tends to increase at a disproportionate rate to the primary voltage rating. Capacitive voltage transformers, or CVTs, are normally used on higher voltage applications. The CVT is basically a capacitance potential divider and consists of the following components: coupling capacitors, typically 10, compensating reactor, step-down transformer, and a ferro-resonance suppression circuit that is found just before the output terminals for connecting to a relay. The accuracy of a PT's operation is specified in the displayed label format. The first item in the label indicates the accuracy class of the PT. The three common accuracy classes are 1.2, indicating PT accuracy between 98.8 and 101.2%, 0.6, indicating PT accuracy between 99.4 and 100.6%, and 0.3, indicating PT accuracy between 99.7 and 100.3%. The next character in the label is a letter designating the burden rating. As previously mentioned in CT selection, the burden represents the total resistance on the secondary circuit. The typical burden designations and their corresponding ratings are as follows. The W rating indicates the PT will operate accurately as long as the burden doesn't exceed 12.5 volt amperes. The X rating indicates the PT will operate accurately as long as the burden doesn't exceed 25 volt amperes. The Y rating indicates the PT will operate accurately as long as the burden doesn't exceed 75 volt amperes. The Z rating indicates the PT will operate accurately as long as the burden doesn't exceed 200 volt amperes. And the double Z rating indicates the PT will operate accurately as long as the burden doesn't exceed 400 volt amperes. If at any time the burden exceeds the PT's rating, the accuracy classification will be compromised. In this example, the PT rated 0.6 double Z would have an accuracy between 99.4 and 100.6%, as long as the burden of the PT remains under 400 volt-amperes.